Welcome everyone to Living Systems 1. This is a core subject in the Bachelor of Agriculture and Technology. My name is Silvana Oconee. I'm the subject lecturer, and I'm also the head of program, or otherwise known as course coordinator, for the Bachelor of Ag and Technology. So you're all doing this subject, Living Systems 1, as it is a core subject. And you may already know, if you attended orientation day, that we actually run two versions of the Bachelor of Ag and Technology. This one here has the course code HEPIBAT, and this is for international students only. This version here is for the La Trobe enrolled students, and the course code is SBATE. So you'll often hear lecturers referring to the SBATE students and the HEPIBAT students. So the two versions of the degree are almost identical, but there are slightly different policies and processes for those two versions. So you'll also notice that there is a different subject code for Living Systems 1. So for the SBATE La Trobe students, here we have the subject code SCI1 LS1. For the international HEPIBAT students, the subject code is BES 109. And that's why you often see two different subject codes on your Moodle subject site for each of your subjects. All right, so as I said, my name is Silvana. Here is my email address. Just note that my surname is Oconee with an I, not an L. And I mention that because lots of students actually make that mistake when they're sending me emails, and then I don't receive the email. So welcome again to Living Systems 1, and now let me just work out what your majors are. Because of course within the Bachelor of Agriculture and Technology you can study a specific major. So could I ask everyone just to type into the chat box, just to type your major in, whether it's agronomy, viticulture and winemaking, sports turf, or equine. All right, so we have a viticulture and winemaking. We've got two viticulture and winemaking, a sports turf, another vit and winemaking, another vit and winemaking. Okay, we've certainly got a big viticulture and winemaking cohort this year, and another vit and winemaking. Okay, terrific. Okay, so our sports turf student, we actually had 3 sports turf students attend the face-to-face today. So I'm sure you'll be keen to meet them at some stage. All right, thank you everyone. And another viticulture and winemaking. There you go. All right, so let's look at the Living Systems timetable. So we're going to go through a fair bit of housekeeping so that you know how the subject runs. But also we'll go through some pointers, not just for this subject, but for all your subjects. All right, so Living Systems timetable, we'll start with the face-to-face classes, even though you guys are obviously doing online, which we call blended delivery, but you may want to 1 week or more come along to the on-campus classes. So if you do decide to do that, they run every Monday, except for next week, which is a public holiday and the campus is closed. Lectures always run from 9 till 11 AM in Building L, room L127. Then we have a tutorial from 12 till 1 in the same room. And then those students that elect to do weekly prac classes, and we'll come back to that in a minute, they'll do their prac class, also in Building L in the lab L109 from 1:15 to 3:15, except for a couple of pracs that actually run until 4:15. So they're pracs that run later on in semester. Then later in the day, and this is optional, I run a student support class from 3:30 to 4:30. So that's often just a very, very small group of students, maybe only 1 or 2 students that just have a few questions or need a bit of help, maybe with, 1 or more concepts. So that's also available to everyone. All right, so you're probably more interested in how the online or blended delivery works. And La Trobe refers to this as blended delivery because we have very few subjects that are actually 100% online. There normally is some requirement for you to attend campus, and that's certainly the case for Living Systems 1. So we will have an online class every Monday evening, and this includes next Monday. So even though it's a public holiday, the campus always closes on public holidays, so we won't have any face-to-face classes, but we still do have our lectures to cover. So the online class will still run. And you're all here, so you know that you access any online class for any of your subjects via the Zoom link, which you'll find on your Moodle subject sites. All right, so online students obviously don't do those weekly prac classes. You will, however, attend a 2-day prac intensive workshop that occurs about halfway or just over past the halfway mark of semester. And we'll come back to that one in just a minute. All right, requirements for this subject. Okay, number 1, you'll need to get yourself a lab coat. So you won't only need a lab coat for Living Systems 1 and Living Systems 2 in second semester. You will require a lab coat for several other subjects. Okay, so organise a lab coat. You can go to La Trobe University in Bundoora. There is a shop there called the School Locker, and you can buy yourself a lab coat there. Here is a place in a shop in Whittlesea called Live, Work and Play, where you can order online through this place, and they will deliver directly to me if you actually indicate the delivery to Melbourne Polytechnic Epping, care of Silvana. All right, so there's plenty of other options. If you do a bit of a Google search online, you'll probably find quite a few places where you can purchase a lab coat. All right, so make sure, please, that you have this before your 2-day prac intensive workshop. All right, if students forget to bring lab coats, I do have a limited number of lab coats for hire. Okay, and there's the cost there, plus your student card, which of course is returned when you return the lab coat. All right, for all prac classes, you will need closed shoes. Before week 5 or 6 of semester, you will need to have just a basic scientific calculator, which you can pick up quite cheap from Officeworks. If you already have a graphics calculator, then that's fine too. All right, we have a question. Do they come in any colour other than white? Yes, they do. They actually do. I have seen the occasional student with a different coloured lab coat. I believe the lab coats from La Trobe, I've only ever seen them in white, but you might be able to find a different colour. Okay, so when you come to class, make sure that you have obviously something to write on. Pens, pencils, rulers are always good. Prac manual. I will be uploading the prac manual to Moodle for Living Systems over the next couple of weeks. Please don't print it out. This will be provided to you. So for students that are doing that 2-day prac intensive workshop, you will receive your prac manuals then. Very handy to have for all your prac classes, for all your subjects, is a fine tip permanent marker. Very useful to label glassware, microscope slides, and so on. Also handy to keep hair ties with you if you've got long hair. Very good to tie your hair back in the lab. Okay, we have another question. With safety glasses, can they be any type? Or is there a specific type that the institution requires or recommends? No, they can be any type. So if you've got a set of safety glasses, for example, that you have in the garage at home, often people do, that is perfectly fine. If you wear reading glasses, then you don't need safety glasses. Okay, we do have safety glasses in the lab that we loan to students. So you don't actually have to purchase a set of safety glasses if you don't wish to. All right, textbooks. We have lots of questions about textbooks. Now, regarding all your subjects, in fact, there are very few subjects that require you to purchase textbooks. Equine students are probably the exception to the rule. Their equine specific subjects do require that they purchase textbooks. For agronomy students, no, I don't believe there are any subjects where you absolutely have to purchase a textbook, even though there are lots of recommended readings. And occasionally there are prescribed textbooks. And that's what we have here. Oh, sorry, for viticulture and winemaking students, there are a couple of subjects. I believe wine chemistry 1, which you do in second year, and maybe another subject where there are prescribed textbooks, and it's highly recommended that you purchase those books. They are very, very useful for that major. All right, for Living Systems 1 and in fact for Living Systems 2 in second semester, which everyone has to do, there are 2 textbooks that you can see here. One chemistry, well, it's chemistry and biochemistry and organic chemistry in the one book. That's why I think it's such a good book. Students have loved this textbook. It's not designed or written in the way that university chemistry texts are often written. They're normally very hardcore chemistry, designed for students that are going to go on and major in chemistry. None of our students are going to go on and major in chemistry. You guys are majoring in agronomy, viticulture and winemaking, and so on. So this is a great textbook called Principles of General Organic and Biological Chemistry by Smith. Then we have this a biology textbook, also very good, and it's called Biology and Australian Focus. All right, they're both prescribed textbooks for both Living Systems 1 and Living Systems 2, but is it mandatory that you purchase them? No, it's not. No, it's not. Most students don't purchase the textbooks. Some students will purchase one or the other, and then you'll have a small number of students that will purchase both. It really is up to the individual. So, for example, if you've never done chemistry before in secondary school, so no year 11 or 12 chemistry, no, you're not given readings from the textbooks. No, not at all. So yeah, some students that don't have any chemistry background, they may purchase the chemistry text, and the same applies to students that have never studied biology, which, believe it or not, can be just as challenging and is often just as challenging as the chemistry if you don't have a background in these topics. What I normally recommend to the students is see how you go for a couple of weeks. If you're finding it a little bit of a challenge, then by all means look at purchasing a textbook, one of the 2 textbooks or both. It's really up to you. If you can find, which you often can find, an older edition of both of these textbooks, that will be perfectly fine. Older edition, secondhand, because really the content changes very little from one edition to the next. You might also want to consider borrowing these textbooks from the library, that is from the Melbourne Polytechnic Library at Epping or the La Trobe Library if you're an S-base student. What else can I say here? Oh, of course, there are lots of different chemistry textbooks that you could borrow from the library, and they have very similar content, But just be aware that many chemistry textbooks don't cover the organic chemistry that you need for second semester. So just make sure that you have, you know, your general chemistry and your organic chemistry in that textbook. All right, so any questions on the textbooks? MP definitely has at least a couple of copies, if the La Trobe University library doesn't. That's odd that they don't have the textbook. Thank you, I'll have to look into that. All right, availability of subject material. And this really applies to all your subjects. So you will always find the lecture notes on Moodle. Normally you will find them from 1 week to the next. They're released 1 week at a time. And for good reason. If we release the whole semester of lectures in one go, it's quite overwhelming. So I normally release the lectures about 6 to 7 days before the actual delivery. So for example, tomorrow, you'll be able to see the lectures for next Monday and so on. All right, hopefully everyone has visited all their Moodle subject sites. That's important, so you start finding your way around each of those Moodle sites, because they're all set up in a similar way, but there are some differences from one site to the other. All right, weekly tutorial exercises will also be posted on Moodle. Prep books, as I said, will be handed to students. Zoom classes, all your Zoom classes will be recorded and made available sometime the next day. All right, just in case you can't attend one evening. And occasionally, I might use pre-recorded lectures. Only occasionally and if I have to. All right, what if you need help with any of your subject material? Definitely for face-to-face students, obviously they can attend tutorials and ask questions then. If you're an online student, it's a bit different. This is where you need to establish a good emailing relationship with your lecturer. I can say that many of your lecturers are happy to email during the evening, on weekends. So if you have any questions at all, please make sure that you're emailing your subject lecturers. You can also request a phone call, and that's sometimes easier to discuss maybe, you know, subject content that's a bit more challenging to do that over the phone. Oh, actually, you've got another option. You could request an extra Zoom meeting, so a private Zoom meeting between the lecturer and yourself. So that's also another option that can be organised. All right, when you're on campus, come past and see me at any time. I'm in building A, room A130A, and all the other full-time lecturers can be found next to my office. All right, student support classes I've mentioned. When you're doing pracs, make sure you really use your prac supervisor's knowledge, okay? Make sure you talk to them about the pracs that you're doing in the labs. And of course, come and see me at any time with any sort of general questions that you've got about your study plan or anything else. All right. All right, class rules probably don't apply to the online students, but if you do attend any classes, just make sure that you've got your mobile phones on silent and observe common courtesy to the speaker. Not usually a problem. Our students are pretty good, many mature age students. So if a student is asking a question and trying to listen to the answer, other students are normally very respectful of that and don't just start talking between themselves. Okay. All right, transition to higher education. So in other words, the transition that students need to make very quickly within the first 2 to 3 weeks from secondary school to a bachelor degree, because there are some important differences, although some of these differences are not as pronounced now as they used to be, say, 15, 20 years ago. Certainly this one is very true. So in secondary school, your time is often quite structured. But in higher ed, it's really about independent learning. So of course your lecturers will teach you, they'll deliver subject content to you, but it's up to you to make sure that you understand the content, and really you have to drive that learning yourself. So it really is about good time management and making sure that you're driving that learning and being organised. All right, this next one is certainly very true too. So in secondary school, the study tasks are fairly evenly spread. In any bachelor degree, you will have many assessments due at the same time, normally concentrated towards the end of semester. So what this means is that as soon as you know what's required for a particular assessment, you need to get onto it as soon as possible. Don't let it sit. Don't let it sit. Otherwise, and this is a trap that many students fall into, they're suddenly faced with all these assessments that are due very quickly and they really don't have time to do them. And it really shows in the work that's submitted. So make sure you're organised, don't delay when it comes to assessments. Semesters are very, very short and they go very quickly. All right, many opportunities for feedback in secondary school, fewer opportunities for feedback. This is certainly true with the large universities because they just have so many students that are doing each subject, you know, maybe hundreds of students in a subject. But we have small classes, so you do get lots of opportunities for feedback and one-to-one sort of assistance. All right, what else have we got here? All right, down here to exams, less emphasis on exams for assessment, more emphasis on exams. This used to be the case, but we did a few years ago start eliminating final exams for some subjects, which really suits many students. Many students hate exams, and that's often not a reflection of their ability. We find that, you know, there's often students that have very, very good understanding of subject content. Best thing you've heard all day. Yes, absolutely. Look, some students, they display a really good understanding of subject content, really good, excellent understanding. They can write about it, they can talk to you about it, but you put them in an exam situation and they basically just go blank and do very poorly. So we have lost exams from some subjects. Unfortunately, not for living systems. You do have a final exam for this subject, but it's not worth a lot. So gone are the days where you might have a final exam or even two big final exams that are worth, you know, up to 90% of the subject mark. That's just horrible. All right, so at the bottom here, well, I don't know why that keeps coming up all the time. Yes, that's horrible. Those big exams, yeah, absolutely. Especially when you have two big exams on the same day and then two big exams the following day. That's just crazy. All right, so just down the bottom, so in secondary school, more frequent tests, exams. In higher ed, less frequent exams covering large amounts of material. This is still the case in some of your subjects, where you will have a final exam, for example, that covers the whole semester. So we haven't lost those exams completely, unfortunately, but that's the way it is. All right, now on Moodle, has anyone seen a document on Moodle, so on the introduction page, called the Subject Learning Guide? And you'll see for some subjects there is a similar document called a subject outline. It's pretty much the same thing. Has anyone seen that? Subject learning guide. Yes? Good. All right, make sure, had a quick look. Okay, great. Make sure that you read through your subject learning guides or subject outlines very closely. Lots of important information in there about the subject. Yes, it has all the assessments in there. It has what you can see on the screen now, this schedule, a learning schedule for the whole semester. It has the prescribed texts, recommended readings, and so on. So basically, all the contact details of the lecturers, subject coordinators. It has our Latrobe, your Latrobe course coordinator, Penny Smith. It has her contact details in there as well. All right, so keep them handy. I just want to show you this part of the subject learning guide, and it is the schedule for the semester. So first thing to note is the week numbers. 1, 2, 3, 4, 5 weeks are shown here. So a whole semester will run for 12 weeks, but that doesn't include the mid-semester break of 1 week. That's not given a week number. So you'll often hear your lecturers refer to week numbers. All right, there we are today, week 1, 2nd of March. All right, next week, week 2, as I said earlier, there's a public holiday, Labor Day public holiday, so there are no face-to-face classes at all for any subjects. The campus is actually closed, but we will still have a lecture that evening. All right, week 3, 4, 5. Now let's go to the next page. All right, there's week 6. And here we have the mid-semester break. There, 1 week off. Now keep in mind that this is a break from classes. It's not a break from your study. In fact, this is a perfect opportunity to really start smashing out some of those assessments, which you will have a fair idea of what you have to do by then for at least some of the assessments. So make sure that this is a really important catch-up week for you. All right, then you come back into week 7 and just look over to the right here. This is when the online mid-semester test will be available at the end of week 7. I'll come back to that in just a minute. Then we go into week 8. Okay, next slide. And here at the top, so this is the end of week 8. This is when the online students, I should say blended delivery students, will actually do their prac intensive workshop on Saturday and Sunday, 2nd and 3rd of May, all day from 9 a.m. until 6 p.m. All right, so keep those dates in mind and keep them somewhere handy to remind yourself. All right, then we go into week 9, 10, 11, 12. After week 12, you will have a study period, usually 1 week, but on occasion it's 2 weeks. And then we move into a 2 to 3 week exam period. That's when if you've got final exams for subjects, that's when they're scheduled. The exam timetable is released at least 4 weeks before the exam period. So you'll be notified when that's available. All right, getting on to assessments, and of course you can find all these in your subject learning guide or subject outline for any subject. All right, let's look at assessment number 1 for living systems. You will at some stage write 2 lab reports. That is a lab report on 2 different pracs. A lab report on 1 prac, which is pre-allocated. I'll let you know which prac you need to write up. And then you'll write the 2nd report on any prac of your choice. Okay. So they are due on different dates depending on whether you are doing weekly prac classes, which actually commence in week 3 of semester, or if you're doing the 2-day prac intensive workshop. All right, for weekly prac students, the first report is due in week 8 of semester. Report number 2 is due in week 12, actually on the last day of semester. For the 2-day prac workshop students, report 1 is due in week 10. and report 2 is due in week 12. So once again on the last day. All right, we have a question. Can someone do the pracs weekly but still do the lectures online? Yes, there is lots of flexibility in this subject. So there are students that do face-to-face classes but have signed up for the 2-day prac workshop. Yep. But weekly pracs, the weekly prac class is full. It is already booked out. So if you really, really need to do those weekly pracs, let me know. But that's going to be a bit tough. That was very popular this semester for some reason. But yeah, certainly get in touch with me. All right, so prac reports. So we'll talk a lot more about prac reports in the next few weeks, you know, how you should write them. I'll provide some examples for you so you can see how they're structured. You will sign up for the prac weekend tonight after class. Okay, so make sure you don't take off after class because I need to sign you up for the prac workshop. All right, so the reports are worth 10% each for a total of 20%. Next assessment, tutorial exercises. So each week I'm going to give you a set of tutorial questions. 6 of those sets of tutorial questions are assessed. Oh, this thing is very annoying. Can I get rid of it? Oh, I didn't want to do that. Okay. All right, can everyone still see the whole screen or not? I don't want that. No. I don't know what I've done there. All right, just give me a minute. Hit the little arrow next to 107%. Is that better? Oh, that's a bit too small. Okay, is that better? Okay, excellent. Thank you. All right, so tutorial questions, 6 sets of tutorial questions are assessed. And as I said, I provide the tutorial questions on Moodle, but you actually submit your answers via the online quizzes, which you'll find in the assessments section on the Moodle site. All right, each set of tutorial exercises is worth 4 or 5% for a total of 25. All right, next we have a mid-semester online test, which will cover only the material that we go over in weeks 1 to 5 of semester. All right, being an online test, you do it from home, it's open book, but having said that, your time is limited. So make sure that you're still prepared and that you don't need to refer to your notes for every single question. Otherwise, you'll just run out of time. All right, so as I said earlier, this will take place at the end of week 8. The online test will open at 6 a.m. on Friday the 24th of April, and it will close on Monday evening at 11 p.m. So that gives you a window of 4 days, and you can start the test at any time during that 4 days. But once you start, then you need to keep going with it because the time the test will shut down once the time expires. All right, so that test is worth 25% of your final mark. Oh, and by the way, all your subjects will require a 50% pass mark, which is nice. You don't have to get 70, 80%, although that would also be nice if you got those marks. All right, so now we head into the final exam, and what's really nice to see, and this is often the case, is that you can actually already be at that 50% pass mark or even higher before you even go into that final exam. It's really good, takes the pressure off, and basically whatever marks you pick up in the final exam, basically just boost your mark to a higher grade. So the final exam is worth 30%, and it takes place during that end of semester exam period. Duration 1.5 hours. So it's quite intense. You have to be very, very well prepared for it in order to, one, complete it, and two, do really well. But there's always some students that do well. It really depends on how much effort you put into that. All right, prac class attendance. So you should aim for 80% attendance of pracs. And remember that some students will do weekly pracs from weeks 3 to 12 of semester, and I'm sure all of you will be doing the 2-day prac intensive workshop. All right, just some general information. So in the next few weeks, you're going to hear about something on Moodle called Turnitin. And you'll see that this is associated with certain assessments, certainly any written reports, essays, and so on. And Turnitin is basically a tool that you use to check your work, to make sure that you're observing what we call academic integrity. That is, that you're referencing properly, that you're not just copying and pasting slabs of information into your written work. As I said, we'll talk a lot more about that, not just in living systems, but your other subjects over the next few weeks. But so Turnitin is really a self-checking tool for the student, but of course your lecturers will also check your Turnitin submission. Keep in mind that you can submit to Turnitin as many times as you want until you're happy with it, and then you actually do the final submission through Moodle. Okay. All right, we'll come back to that one later on. All right, when it comes to referencing, I'm going to show you in the next few weeks this great referencing tool, which we have on the Melbourne Polytechnic Library website. It's called Ernie Easy Referencing. And it allows you to select the right referencing style, and we use Harvard referencing, and it allows you to see how you should reference a particular source of information depending on whether it's a textbook, whether it's a web page, or a journal article, and so on, and how to reference images that you're using in your work. All right, feedback on any assignment drafts. So your lecturers will be happy to look at an early draft of your written work as long as you send it to them early enough. So for living systems, make sure if you want me to check a draft of your work and give you some early feedback so you can make improvements before you submit it, make sure that you send it to me at least a week before the due date. Okay, if you're sending drafts the night before it's due, then you're not going to get any feedback. It's just really too late. All right, here's another tool that could be useful. It's called Studiosity. You'll find this on every Moodle subject site. And this is where you can actually submit your work. It doesn't come to your lecturers, but it does go to expert tutors. They will actually assess your work. They'll give you some suggestions to improve, for example, the grammar, spelling, and so on. And then they send it back to you within 24 hours, sometimes within a couple of hours. So that's free to our students. All right, we've talked about prac attendance requirements. International students must attend all their classes, okay, face-to-face. All right, so no missing classes and listening to recordings, because I do have to record attendance for international students. All right, that's part of their visa requirement. All right, census date. Keep census date in mind. Census date is the last day during semester from which you can withdraw from a subject and not incur a help debt for that subject. Okay, so census date is generally the end of the 4th week of semester. You can find these dates online, either on the La Trobe website for SBATE students or on the Melbourne Polytechnic website for HEPIBAT international students. All right, so if you realise by week 4 that you might have taken on too big a load, a study load, then you certainly can withdraw from one or more subjects before census date. You can withdraw after census date, but you will still incur a help debt for that subject if you withdraw after census date. All right, academic integrity I've already referred to. So it basically means being honest in your academic work and acknowledging the source of information. And of course, we do that by referencing. Okay, we have a question. What if you wanted to add a subject and not withdraw? You can enrol in any subject up until the end of the second week of semester. Okay, so if you want to add a subject, make sure you do it by the end of next week. After that, it's too late. We used to allow that in the past, but we find that it's just too hard for students to catch up. So end of week 2, that is the cutoff. All right, so still on academic integrity. So for the La Trobe SBATE students, make sure, please, that you complete this module called the Academic Integrity module. Here's the actual code, LTU0AIM, and you will find this on your La Trobe LMS, your La Trobe Learning Management System. Okay, so make sure you complete that. Complete that as soon as you can before all the work really starts heating up. I say here, complete this in the first 3 weeks of semester. That will be fine. So at least you're prepared going into your early assessments. All right, for still on the La Trobe SBATE students, you will also see on your Melbourne Polytechnic Moodle site an academic integrity module tile. Please ignore that. You don't need to complete that one, but you do need to complete the La Trobe one. All right, the academic integrity module that you can see on your Moodle site, this one must be completed by our HEPIBAT international students. Okay, once again, please make sure you complete that within the first 3 weeks of semester. I would get onto it straight away. All right, so why do we study chemistry and biology? So obviously Living Systems 1 and Living Systems 2 basically cover some general chemistry, a bit of biochemistry, some biology, and in the case of Living Systems 2, some organic chemistry. Now, students normally have no problems understanding why they have to study biology. Seeing the relevance to any of your majors is straightforward, but sometimes it's hard to see where the chemistry fits in. So just looking at the images on this slide and thinking about your own specific major, why do you think you would need to know a bit of fundamental chemistry? Why do you think, or how do you think that some basic chemistry would help you in your chosen major? Looking at these images here, soil composition, absolutely. Everyone, oh sorry, not everyone, most majors will actually do some soil science eventually in their degree. And of course, to really understand the soil science, you have to know some basics in chemistry. Okay, what do we have here? Reactions between sugars and yeasts. Absolutely. Absolutely. So anyone studying viticulture and winemaking will also study wine chemistry 1. And to really appreciate wine chemistry 1, you must have Living Systems 1 and Living Systems 2 chemistry. And all students that have come and gone before you have said all the chemistry concepts in Living Systems 1 and 2 are very important moving forward into wine chemistry 1. So yeah, definitely. All right, so you could also think about nutrition. So plant nutrition or animal nutrition really requires a bit of an understanding of chemistry to understand that. And even down here, so everyone's familiar with absolutely photosynthesis. everyone knows, you know, a bit about photosynthesis, maybe a lot about photosynthesis, but to really have a deeper understanding of that process, that crucial process, you need to know some chemistry. And we will do a bit on photosynthesis in living systems too, but then next year in plant physiology, you'll learn that process, that incredible process, in a lot more detail. All right, so we study chemistry and biology to understand the fundamental underlying principles of animal physiology. We didn't talk about animals, plant physiology, soil science, the environment, nutrition, both animal and plants, and so on. So you will see that chemistry popping up basically in lots of other subjects. The chemistry in Living Systems 1 and 2 is probably less important going forward for equine students. Definitely very important for the other majors, but the biology is very important for everyone regardless of the major. All right, so why do we combine chemistry and biology into the one subject? So, all right, here we have another question. Will we have to learn the individual compounds in the Calvin cycle for living systems too? No, you do not have to memorise each of the substrates. Yeah, no, that's just nasty and not necessary. You will need to have an understanding of the cycle. So what the purpose of the cycle is, you know, maybe the inputs and outputs of the Calvin-Benson cycle, but not to know all the substrates. No, that's reserved for the good old days of biochemistry. I don't know if they still do that these days. All right, so traditionally, and actually even today, chemistry is delivered in all universities, probably all universities, as a standalone subject. That's certainly the way that it's delivered in the other La Trobe university degrees. It's a standalone subject and it's delivered by members, academic members of the chemistry department. Biology is a completely separate subject and it's delivered by academics from various biology departments. And members of those different departments are very protective over their own subjects. That's obviously a source of income for them, but they also specialise in those areas, so that makes sense. But the problem is with that system is that it's difficult to link the concepts from chemistry to biology when they're being taught as standalone subjects. So about 10 years ago, one of our academics thought it would be a great idea to combine our chemistry and biology subjects together into the same subjects, into two subjects basically. I was sceptical, I didn't think it would work, but after the first year I was convinced. It really, really does help. And that's because just about every biological system you look at, oh, they do overlap, absolutely. Just about every biological system that you look at, that is if you go into, a deeper level, those systems are driven by underlying chemistry. So it's really important. I think it works very well to have them in the same subject. And here we have some great examples here. So photosynthesis, once again, everyone's familiar with what that is. To really understand photosynthesis, you have to know the chemistry that's going on in this structure here. Does anyone know what that structure is called? And that's found in most plant cells. This green structure, the chloroplast. Yes, absolutely. This is where photosynthesis occurs. So you really have to know some underlying chemistry to appreciate that incredible process. So metabolism of sugars and fats. So when we're eating food, how are those sugars and fats actually metabolized to generate energy? But it doesn't just apply to animals, that also applies to plants. Plants also metabolize sugars and fats to generate energy. And where does that take place? In these structures here that are found in most animal and plant cells called mitochondria. All right, in order to understand the structure and function of certain biological molecules. So, for example, proteins, you really need to know some chemistry. So this is what we're looking at here. So this structure here, this is the basic, or one of the basic building blocks of a protein, and it's called an amino acid. If you haven't studied this before, you'll be looking at this structure and saying, what on earth is that all about? It won't really make any sense to you. But once you've done a bit of chemistry, well, in particular biochemistry, then everything that you see here will make perfect sense to you. All right, so that's it for all our housekeeping. Does anyone have any questions? We're going to have a very short break, and then we're going to move on to our lecture for tonight. Any questions, or is everyone happy with that so far? No, all good? All right, everyone else good? Happy? Happy? Oh, we've got a few more students on. That's great. Good. All right, very good. All right, let's have a break. Is everyone happy with a 5-minute break? Or would you like a little bit longer? Time for wine. Yes. I need to try that. Have a wine while I'm delivering lectures. 5 minutes is fine, yeah? Everyone happy with 5 minutes? 5 minutes good? All right, great. Go and get your wine or your beer or your coffee, and I'll see you in 5 minutes. Okay, I hope everyone's back online. We have a question. Semester 2. All right, we have 2 questions. So the first one, did you say the tutorial questions for each week are the same as what is in the online quiz each week? Yes, that is correct. So the tutorial questions that you see on Moodle are exactly the same as what you will find in the online quiz. But just watch out, sometimes the multiple choice answers in the online quiz may shuffle around a bit. So what students normally do is they work through the tutorial questions, through the hard copy, and then jump onto the online quiz to submit their answers. But look out for those shuffling answers. But yes, they are exactly the same. And we have another question. In semester 2, will Living Systems 2 probably be on Mondays starting at 6:30? Yes, definitely. Living Systems is always on a Monday and always at the same times. So you can certainly organise ahead for that subject. All right, let's move on with lecture 1, matter and measurement. So in this introductory lecture, we're going to cover quite a few different concepts. Some of those concepts I'll just introduce them and then come back to them and expand on them in later lectures. Other concepts we cover just because they're traditionally covered in chemistry, they may or may not be useful going forward. Some concepts are very important going forward into your other subjects. And I try to let you know as we go along what's important and what you really don't have to take too much notice of, apart from answering tutorial questions, that is. Okay, and of course, different concepts are important for different student cohorts, depending on your major. All right, so let's begin, and we will begin with a very simple definition of chemistry. What is it? Chemistry is the study of matter, its composition, its properties, and transformations. That is how one substance can transform into another substance. So what do we mean by the term matter? Matter is anything that has mass and takes up volume. And we'll come back to this interesting term mass just a little bit later on. Of course, we can have matter that's naturally occurring, for example, cotton or sand, and we can have synthetic matter, man-made matter, such as nylon. All right, everyone is familiar with the 3 major states of matter. That is solids, liquids, and gases. And I will just introduce this here, and then we'll certainly come back to this in a later lecture in more detail. So let's start with the solid. A solid has definite volume. It maintains its shape regardless of the container that you put the solid in, and it contains particles, which you can see here, particles that lie very close together in a very regular 3-dimensional arrangement. So that's not to say that they don't move. All particles do move, but these particles don't move past each other. They basically just vibrate in situ, if you like. All right, a liquid also has a definite volume, but it will take on the shape of the container that you place it in. And it also, just like a solid, has particles that are very close together, but these particles will move quite randomly and can slide past each other. Now we come to a gas. Gas has no definite shape or volume. It will expand to fill the volume and take on the shape of whatever container you place it in. A gas has particles, consists of particles that are very far apart and move around randomly. And you can see that the space in between the particles is often larger than the size of each particle itself. All right, so we'll come back to the states of matter in other lectures. Now let's move on to different ways that you can categorise matter. So firstly, we can talk about physical properties of matter, and we can talk about chemical properties. And in the same way, we can talk about physical change or chemical change. So let's start with physical properties. Physical properties are those properties that can be observed or measured without changing the composition of the material. So you're not actually changing the identity of the particles within that material. Here are some physical properties or physical changes that can be applied. We can look at boiling point, we can look at melting point, solubility, colour and odour. These are the main ones. Colour and odour, viticulture and winemaking students will look at these two properties in their wine classes. So we won't look at these, but we will certainly revisit boiling point, melting point and solubility. All right, so physical change will alter the substance without actually changing its composition, without changing its identity. And here is an excellent example. And we start off with a solid. So this is solid water, in other words, ice. Let's apply a physical change, such as melting. That will actually result in a change of state, changing the state of matter from a solid to liquid water. Let's apply another physical change, for example, boiling, and that will result in another change in state of matter from a liquid to a gas, in other words, water vapour. The molecules themselves, the water molecules themselves, remain unchanged. Okay, so we're not altering the identity of those particles. We're simply changing the state of matter. All right, so now let's look at chemical properties. So chemical properties will determine how a substance is converted into another substance. And this always involves a chemical reaction, chemical change or chemical reaction. And here are some good examples. So if we think about a piece of paper burning, so firstly, what sort of reaction is that? What sort of chemical reaction when you're burning something? Well, not when you're burning it, when something's burning. Does anyone know what sort of reaction that is? Very, very common reaction. So the reaction, chemical reaction that involves burning. Combustion, that's the one. That's the one, that's a combustion reaction. All right, but think about that process of burning. Of course, that paper, it's derived from plant material. So it contains carbohydrates, and carbohydrates contain lots of carbon and lots of hydrogen. And in the process of combustion, the carbon and the hydrogens are released. They combine with oxygen in the atmosphere to produce carbon dioxide and water vapour. So in other words, you're completely changing the identity of that substance in the combustion process. So that's an example of chemical change. Metabolizing an apple for energy. So when you eat an apple, those sugars are extracted and they are chemically converted in such a way that your cells can produce energy. So that's another example. Oxygen and hydrogen combining to form water. So that's an example that's illustrated here. So we can see in red, two oxygen particles joined together. This is how you would normally find oxygen in the atmosphere. And in white, we have two hydrogen particles joined together. Once again, that's atmospheric hydrogen. Most hydrogen you'll find in that form. In order to split those particles apart, you need a chemical reaction to occur, to actually break those bonds that hold them together and then to rearrange them and form new bonds to produce molecules of water. So that's also an example of chemical change. All right, now we're going to look at another way that we can classify matter. So all matter can be classified as either a pure substance or as a mixture. So let's start with pure substances. Pure substance is composed of a single component. It has a constant composition, regardless of the size of the sample, regardless of where you get that sample from. Most importantly, and highlight this one, Pure substance cannot be broken down to other pure substances by a simple physical change, that is by boiling or by melting. Okay, so keep that in mind for one of your tutorial questions. All right, a couple of examples here of pure substances. Here we have sugar. So these coloured molecules here, that's one sugar molecule. That's another one there. And here we have water. Okay, so they're both examples of pure substances. All right, a mixture is composed of more than one component, and it can have varying composition, that is any combination of solid, liquid and gas, and a mixture can be separated into its components by applying a physical change. So if we take this example of a mixture where we have sugar dissolved in water, that's what we're seeing here. So these particles are the sugar molecules, and the rest of it that's a little bit sort of faded, they're the water molecules. So this is an example of a mixture, and of course you could separate the water from the sugar molecules simply by slowly evaporating the water off and collecting it in a separate container. All right, sorry, I'm just going to go back. So pure substances can be further sub-categorised. And here are the two categories on this slide. Elements and compounds. So an element is an example of a pure substance, but it can't be broken down by a chemical change. And an example here is pure aluminium metal. And it's interesting that, and we'll talk a lot more about elements next week, it's interesting that there's only about 118 elements known to man, only 118. But compounds, on the other hand, and compounds are also pure substances, but they're formed by chemically combining two or more elements. There are many thousands of compounds that are known to man. So quite incredible that there is actually so few elements that are known. All right, so let's look at this example of a compound. So we can take two elements. First one is sodium, which are the grey particles, and the next one is chlorine, or rather chloride, which are the green particles. And they combine in such a way to form sodium chloride, which you probably know is your common table salt. And of course, here are the abbreviations for sodium, Na, and chlorine, or chloride, I should say, Cl. And you'll learn these abbreviations as we go on. So here's the abbreviation for aluminium, Al. All right, we have a question. How far will we go into the periodic table? To which number or element? We are going to stick to the top 4 rows, 4 or 5 rows of the periodic table, and that is it. Because when it comes to biological systems, they're the elements that we're really concerned with. So definitely don't go and memorise the periodic table, okay? Don't memorise any of it, in fact, because you won't need to. Even when you need the periodic table in the final exam, for example, you'll actually be provided with a copy of the periodic table. Oh, you already have memorised it from high school. Oh, very good. That's good. You won't even have to refer to the periodic table at all. All right, we'll talk about that next week. Periodic table is amazing. All right, so here's a summary of what we've just talked about so far. So we started with matter, and matter can be categorised either as pure substances or as mixtures, and then pure substances can be either elements or compounds. All right, now let's move on to a different topic. We're going to talk about measurements. Now, regardless of your major, you are going to be taking measurements of something. Give me some examples. Give me some examples relevant to your major of what you might be measuring. What do you think you might be measuring that's relevant to your major? Distance between vines and rows. Absolutely. Gravity. Oh, gravity. Measuring gravity. I have to think about that one. It's a good one. Making measurements in wine. Yes, absolutely. You'd be measuring, yes, alcohol. Alcohol content, pH, titratable acidity, applied nitrogen. Yes, so you've got lots of examples there. Okay, very good. All right, so measurements. That's a given that you'll be measuring something. And on a regular basis. So of course, every measurement is composed of a number and a unit, and the number itself is meaningless without a unit. So of course, we always use units when we're reporting measurements. So for example, if you were told to take an aspirin dosage of 325, that would be meaningless. Does that mean milligrams or grams or tablets, and so on? All right, so you may be a little bit familiar with the English system, which uses units like feet for length and gallons and pounds and so on, but that's not commonly used. It's still used in the US, of course, but they're slowly coming around to our favoured metric system. And the metric system is great because there's this systematic relationship between the units, so you don't need to memorise everything. And the metric system uses units like metres and litres and grams and so on. So that's familiar to everyone. What might not be familiar to you is that each type of measurement has what's called a metric base unit. So looking at this table, for length, the metric base unit is the metre. For mass, it's the gram. For volume, it's the litre, and so on. And of course, here are the symbols for all those units. All right, so what does that mean? What's the meaning of that metric base unit? Other units, all other units for that particular type of measurement are related to that metric base unit. So let's take an example of, let's take this example of the gram, the metric base unit of the gram, and see how everything else relates to that. All right, back to this table. So in this table, we have common prefixes in this column here that are used for metric units, and you'll certainly be familiar with some of them. Kilo, for example, and milli. Micro, this is something that we use quite often, so get used to this one. And we definitely don't go down to nano. All right, so how does that relate to the metric base unit of gram? So let's say you had a measurement that was in kilograms. Kilo, the prefix kilo, means 1,000. So that's telling you that a kilogram is 1,000 times larger than the metric base unit of the gram. Let's say you had a measurement that was milligram. The milli, the prefix milli, is telling us that a milligram is 1,000th, 1,000th of the metric base unit for gram. Okay, so here are the meanings of those prefixes. Okay, and here's the numerical value. And in this column, we have what's called scientific notation. We'll come back to that later on. All right, so milli. So this one here, micro, this is a good symbol to get used to if you're not used to working with microlitres or micrograms, because that's something that you will come across. All right, so here are just some relationships between different units in measuring length. You don't have to memorise any of this. Measuring mass. All right, so let's just talk here about that term mass and a very similar term, weight. And we often use these two terms interchangeably, and we'll continue to do so, but they actually have different meanings. So mass is an actual measure of the amount of matter in the object. which means that that's independent. It's independent of where you're actually measuring the mass, the location where you're measuring mass. So if you take a measure of mass of an object on Earth, and it will actually have the same mass when it's on the moon. There'll be no difference. But weight, on the other hand, will be different depending on where you weigh the object, because weight is the force that matter feels due to gravity. So if you weigh yourself on Earth, weigh yourself on the moon, you'll be much lighter on the moon, won't you? Because of the gravitational force is much less on the moon. All right, so slightly different meanings there, well, actually quite different meanings. But of course, in a practical sense, we weigh objects. So we'll keep using those terms interchangeably. All right, and here are some measurements of volume and some relationships there. All right, now let's move on to a new concept. And here we're looking at exact and inexact numbers. So what do we mean by that? An exact number results from counting objects, or it's part of a definition. So for example, if you counted the fingers on your hands, you would most likely count 10 fingers. And that is an exact number because you will have exactly 10 fingers, not 9.6 or 10.2, but exactly 10. So that's an exact number. Here's an example of a definition. 1 metre equals exactly 100 centimetres, not 100.02 or 99 point something. All right, so they're exact numbers, but we usually deal with inexact numbers, and these are numbers that result from any measurement, any type of measurement or observation. And inexact numbers always contain a certain degree of uncertainty. So let's look at some examples. 15.3 centimetres, that's a measurement, 1,000.8 grams, and 0.0034 mil. They're all measurements, so they are all inexact numbers. So where does that uncertainty actually come from? Let's take, for an example, a measurement involving length. You measure something using a 30 centimetre ruler, for example, and you come up with the answer of 10 millimetres. But what if you measured the same object under the microscope using a high precision graticule unit? You would not get 10 millimetres. You will get something like 9.853 or 10.374. It'll be a much more precise measurement compared to the measurement with the 30 centimetre ruler. So that's where the uncertainty arises from. It's basically how accurate the measuring instrument is. But even then, you will never be exact. How many decimal points do you have to go to actually have an exact measurement? We probably don't even have that sort of technology available. All right, so they're inexact numbers. Now, knowing that, we can actually determine significant figures in any measured number. All right, so what are significant figures? Significant figures are all the digits in a measured number, including one estimated digit. And that estimated digit is usually the last digit in the actual measured number. All right, so let's look at some examples. Keep in mind, all non-zero digits are always considered to be significant figures. So if we take this example of 65.2 grams, how many significant figures are there in this measured number? Well, there's no zeros in there, so we have 1, 2, 3 significant figures. Again, no zeros here, so how many significant figures? There's 6 significant figures. Which one is the estimated digit? In this case, the 5 is an estimation, and in this case, the 2 is the estimated digit. So they're all straightforward. But what happens when you have zeros in the measured numbers? Then you have to apply one of two rules. So rule 1 states that a 0 counts as one of the significant figures when it occurs between two non-zero digits, which we can see here, 29.05 grams. So that 0 is counted as a significant figure. So we've got 4 significant figures there. Those zeros are also sitting in between non-zero digits. So here we have 5 significant figures. A 0 also counts as being significant when it's at the end of a number and that number contains a decimal place. Okay, so we've got a decimal here. So those zeros are at the end, they count as being significant. Here we've got a decimal, so that 0 counts as being significant. All right, when does a 0 not count as being a significant figure? It doesn't count when it occurs at the beginning of a number. So if you're presented with this 0.00245 milligrams, you would say it has 3 significant figures. You wouldn't count these zeros at the beginning. That doesn't mean that you can remove them. That's where some students get confused. In this example, we only count the 8 as being a significant figure. And a 0 doesn't count as being significant when it's at the end of a number that does not contain a decimal. So 2,570, we don't count that as being significant. We say this number has 3 significant figures. And this one on the right has 5 because we don't count those zeros at the end. All right, so that's significant figures. Not particularly important going forward into your other subjects, but it's certainly something that is always taught in chemistry. So at least you've got some awareness of it, even though it's not really that useful. All right, so there are rules for multiplication and division, and these rules basically tell you how many significant figures you should have in the answer to an equation. So for multiplication and division, the answer will have the same number of significant figures as the original number in the equation with the fewest significant figures. So for example, if we look here, 351.2 divided by 5.5. So this number here has 4 significant figures. This one here has only 2. So that means you should report the answer, which happens to be this, using only 2 significant figures. All right, and there it is there. So in this case, you would have to round off to get that down to 2 significant figures. And I'm sure everyone's familiar with the rules for rounding off. All right, and here are the rules for addition and subtraction. So when you're adding or subtracting, the answer will have, or should have, the same number of decimal places as the original number with the fewest decimal places. Here's the example, 10.11 divided by 3.6. We've got 2 decimal places here, only 1 decimal place here. So the answer should also be reported with only 1 decimal place. So rather than 6.51, the answer should be 6.5. All right, moving on, a new concept. Now this one is more important, a lot more important, because you'll come across numbers often written using scientific notation. Is anyone familiar with how to write standard numbers, normal numbers using scientific notation? Is anyone familiar with this? Yes, someone is. You did that in maths in high school. Very good. Yeah, some students, there's always some students that are very familiar with this and then others that have never come across it before. Oh, we've got a few yeses tonight. Excellent. All right, but we might have a few no's. So let's go over this again. All right, so in any of the sciences, you often come across very, very large or very, very small numbers. So scientific notation is really a way to abbreviate those numbers. And in scientific notation, a number is written, as you can see here, y by 10 to the power of x, where y is called the coefficient, and the coefficient is always a number between 1 and 10. And then this little x is called the exponent, and it's any positive or negative whole number. Keep that one in mind for one of your tutorial questions. Now, anyone that studied physics will say, oh, but we can use fractions as the exponent. That is true in physics, but we don't do that in chemistry. So a bit of a difference there. All right, so y times 10 to the x. Now, for anyone that hasn't done this before, everyone else just bear with me. This can be a little bit tricky if you've never done it before. All right, so let's consider something like this. All right, 10 raised to the power of 2. What does that mean? What does that mean, 10 raised to the power of 2? 10 times 10. So 10 multiplied by itself 2 times. So that equals 10 by 10. Okay, which equals, I should say that equals 10 times 10 is 100. All right, good. Now, what if we wrote that as 1 times 10 to the 2? What if we wrote it in that way? 1 times 10 to the 2. What would that mean? The same thing, exactly right. It's exactly the same. It's still 1 times 10 by 10. It's still going to give you 100. Exactly right. So 1 by 10 to the 2. This is an example of 100 written in scientific notation, and 10 to the 2 is just a shorthand of that. Okay, so it means exactly the same thing. All right, let me just clear that. Otherwise it carries on to the next page. All right, so let's look at how we convert a standard number into scientific notation. Let's work through these examples. Once again, bear with me if you know how to do this. So let's start with here, this number on the left, 2,500. You're being asked to write that using scientific notation. Where do we start? Some very simple steps which you can follow. Step 1, move the decimal point to create a number between 1 and 10. Okay, so if we say the decimal point must be here, yep, and we move that, we want to create a number between 1 and 10, so we're going to create the number 2.5, 1, 2, 3. Going to put a decimal point in there, and that will give us a number of 2.5. 2.500. Then what do we do? Step 2, multiply the result by 10 to the x. Multiply, we don't actually multiply it, we just write multiplied by 10 to the x, where x equals the number of places the decimal was moved. So what did we do? We moved it 1, 2, 3 places. So this exponent becomes the number 3. Okay, and because we moved that decimal to the left, this number will be a positive number. So now we have 2,500 written in scientific notation. How does that sound, everyone? Give me a yes or a no. Or all good. So I've got a good, all good, yes, Easy. Yep. All right. Terrific. Let's look at another example. And I'll clear that. All right, let's look at this example now. 0.036. Once again, what do? Move the decimal point to create a number between 1 and 10. So we will go 1, 2. Put the decimal point in there, which will give us a 3.6. 3.6. And then we just write multiplied by 10 raised to the power of x, where x is the number of places that we moved the decimal. We moved it 2 places, but because we moved the decimal to the right, that becomes -2. And so there we have it, 0.036 written using scientific notation. All right, let's clear that. Move to our next slide. So here we have the reverse. The reverse of that is taking a number that's already in scientific notation and converting that back to a standard number. So when the exponent x is positive, which we can see in this example that we've been given, 2.800 by 10 to the 2, when the exponent is positive, then we move the decimal point that many places to the right. So here's the decimal, we move that 1, 2 places to the right, put it in here, and that gives us the number 280.0. So we've gone from this scientific notation back to our standard number. Now, when the exponent x is negative, which is what we have in this example, -2, scientific notation, 2.80 by 10 to the -2. When that's negative, then the decimal point here is moved to the left. So we take that decimal, move it 1, 2 places. I need my pen. 2 places. So we put the decimal here. And we have to put a 0 in there. Yep. And the number becomes, or we can put a 0 in front of the decimal, 0.0280. And that's what we have there. Okay. All right, so you get to practice that in your tutorial questions. All right, so make sure that you're familiar with scientific notation and going both ways, from a standard number to scientific notation and the other way also. All right, so that's an important one for everyone to know. All right, now when you're converting a quantity from one unit to a different unit, some students can do this very quickly, very easily. Other students need a bit of a method that they can use to do the conversion. So this is not something that you'll have to do a lot. Viticulture and winemaking students, you will do this a little bit in wine chemistry. But for those students that need a system that they can follow, some rules, this factor label method is quite good. It utilises conversion factors. And if we look here, we can see this is the original quantity that you have. And if you multiply that by a particular conversion factor, then you will have a desired quantity using the desired units. Okay, you'll have that conversion. The conversion factor itself is written as an equality. So for example, 2.21 pounds equals 1 kilogram. But to use this conversion factor, you have to express this as a fraction. So that fraction could be written in this way, 2.21 divided by 1, or the other way around, 1 divided by 2.21. So how do you know which way to actually express that fraction? Let me just clear those drawings. How do you know which of those fractions to use in your problem solving? Let's just move to here. All right, so here's what you're trying to convert. You have this measurement, 130 pounds, but you want to convert that into kilograms. Okay, so you're going to multiply this by your conversion factor. So do you use this one here, 2.21 divided by 1, or this one at the bottom? You will choose this one, and that's because the measurement with your unwanted units, that is pounds, is at the bottom. Okay, so you choose this one, and that's because you can actually cancel the pounds there with the pounds here. You can cancel them out, and that leaves you with the desired unit of kilograms. All right, so once that's set up, you just multiply 130 by 1 divided by 2.21, and that will give you your desired number, or your desired units, rather. All right, so it's quite a good system, this one, if you need to do conversions. And here's an example, so if you'd like to practice that, certainly work your way through this example. All right, moving on to another concept, the concept of temperature. And this is also very important for all student cohorts, regardless of major. All right, so temperature, very simply, is a measure of how hot or cold an object is. Here are the 3 temperature scales that are used. Everyone's familiar with Fahrenheit, degrees Fahrenheit, of course Celsius, degrees Celsius. Some might not be that familiar with Kelvin, the Kelvin temperature scale. And just note here that Kelvin, we don't say degrees Kelvin, we just say Kelvin, unlike degrees Celsius and degrees Fahrenheit. Here are the conversions from one temperature scale to the other. The most important one that you'll be using going forward, well, at least in living systems, one is to be able to convert from degrees Celsius to Kelvin. And it's a very simple one. To convert from degrees Celsius, you simply take the temperature in degrees Celsius, add 273, and the answer will be expressed in Kelvin. So a really simple one, that conversion. All right, let's do a little bit of a comparison of the 3. Oh, when is Kelvin used? All right, the question is, when is Kelvin used? So Kelvin is often used in the sciences, and you'll see later on when we're talking about relating parameters such as pressure, temperature, volume, number of moles, that's when we tend to use Kelvin. Okay, and you'll see that in a later lecture. All right, so let's look at, do a bit of a comparison here of the 3 temperature scales. And this one, of course, we're all familiar with, the Celsius scale. I've got Fahrenheit on the left and the Kelvin scale on the right. All right, so if we look at the Celsius scale, we're all familiar with 0 degrees Celsius, which is the freezing point of water. If we look at the equivalent point on the Kelvin scale, we have 273 Kelvin. So that probably gives you an idea as to why on the previous slide, where this 273 comes from in that conversion. Okay, so on the Kelvin scale, where does 0 Kelvin sit? It sits right down here, and that's equivalent to negative 273 degrees Celsius. And the reason that they put a 0 Kelvin down here is because that is the theoretical absolute zero, what we call absolute zero. Does anyone know what that refers to? What does that temperature absolute zero refer to? 0 Kelvin or negative 273 degrees Celsius. Absolute zero. So this is a theoretical, exactly right. So this is the temperature at which all atomic movement, all molecular movement is thought to cease completely. And of course, if there's no molecular movement whatsoever, then there is absolutely no heat generated. So it's thought to be basically the coldest. Of course, that's still a theory. All right, so that explains why 0 Kelvin is set down here. Now let's look at the difference between 0 degrees Celsius and 100 degrees Celsius. Obviously, the difference there is 100 degrees. If we relate that to the Kelvin scale, the difference between 273 and 373, we have 100 Kelvin units. In other words, 1 degree Celsius is exactly the same size as 1 Kelvin. Okay, that's not the case when we look at the Fahrenheit scale. So between here and here and here and here, we have 100 units, but between this point on the Fahrenheit scale and this point, we have 180 degrees Fahrenheit. So 1 degrees Fahrenheit is not equal in size to 1 degree Celsius or 1 Kelvin. All right, we will come back to temperature in some form. So do you not convert Fahrenheit to Kelvin, as there was no conversion equation? No, we don't do that in Living Systems 1. We don't need to do that conversion. We very rarely, if ever, use Fahrenheit, even though I think that there is one tutorial question just for the purpose of using those conversions. All right, our final concept here is that of dilution, another concept that everyone's familiar with. Dilution, of course, is the addition of a solvent such as water to decrease the concentration of a solute, such as salt, for example. The solution volume changes, but the amount of solute is constant. And you can see that here's our initial solution with 10 particles. In there, we dilute it by adding more water, same number of particles, but the volume has increased, so the concentration has decreased. All right, so a very useful formula when you're looking at dilutions is shown here. C1V1 equals C2V2. All right, what does that mean? C1V1 refers to the concentration and volume of the initial solution. Okay, that's your starting solution. C2V2, concentration and volume of your final diluted solution. So if you know 3 out of 4 of these values, then we can solve for the unknown value. Let's look at an example. What is the concentration of a solution formed by diluting 100 ml of a 5% salt solution to 200 ml? All right, if you haven't used this type of formula before, make sure you write it out in such a way, as you can see here, and then carefully dissect that question so that you can determine the value for C1, V1, C2, and V2. Well, 3 of the 4 anyway. All right, so we're diluting 100 ml of a 5% salt solution. So this is your initial concentration and volume. Okay, this one here. All right, so that means C1 is 5% and V1 is 100 ml. We're diluting that solution to 200 ml. So here's your final volume, or V2, 200 ml. We want to know what the concentration of that final solution is. So C2 is your unknown, and hence the question mark there. All right, so once you've done that, all you need to do is rearrange the equation. And we rearrange it so that we get C2, our unknown, on one side of the equation by itself, and that way we can solve the equation. All right, so once that's rearranged, we will end up with C2, our unknown, equals C1 multiplied by V1, and then divide that by V2. All right, for anyone that's not really comfortable with rearranging equations, there's a really simple way of doing that. And I'll show you right here. C2 versus, oh, all right, get rid of that one. C2, C2. There you go. So we said that C2 was our unknown. That's what we're trying to solve for. So that's our question mark. Okay, so to rearrange the equation so that that's by itself on one side, we simply leave that one where it is, take this one, we're trying to get rid of that, and just transfer it so that it's under the other side. Okay, that's all you need to do. Put the V2 under there. And now we can solve that because we can see that C2 equals this multiplied by this and then divided by that. Okay, so use that very simple method to rearrange all the equations that you're going to come across. And we don't do too many in this particular instance of chemistry. There'll only be a few equations that we'll be looking at. But if you use this same system, then you can't go wrong. All right, so make sure you work your way through this. So C1V1 multiplied by V1 was 5 multiplied by 100, and then you divide by 200. And of course, when we're solving any equation, make sure that you cancel any like units. So we've got mil there and mil there, so cancel them out. That leaves us with percentage. What are we trying to solve for? We're solving for concentration. And in this case, our concentration is in percentage. So if you see that that's the remaining unit after you've done your cancelling out, then you know you're on the right track. And the answer should be 2.5%. All right, sorry. So we have another question. Or more. So divide both sides by V2 to cancel it out on the right side. Yes, absolutely. Yep. That's exactly what you do. Yeah, this method here is just a simple method. Yep, that's exactly right. Yep, so what someone is saying is that if you're actually using your maths that you learn in secondary school, C2, V2, to actually do the rearranging, okay, you would divide both sides by this value that you're trying to get rid of from that side of the equation. Yeah, V2. Okay, divide both sides by V2, and on this side, you can actually cancel that out. So you're left with the same thing, this rearranged equation of C2 equals C1V1 divided by V2. Yep, absolutely right. All right, so you'll have some practice questions in your tutorials. And I think we've got one more example. Here we go. One more example, and this is probably a more, well, it is actually a more realistic example of what you might need to work out. All right, so the question, how many mil of a 2.5% salt solution would be needed to prepare 25 mil of a 1% solution? So this is very common, where you would take a concentrated solution that's been made up, and then you'll perform a dilution to actually make up the concentration that you required. So your working solution. Start with stock solution, and then you would prepare a working solution. All right, so let's dissect this. So you're being asked for volume, how many mil? You have already a 2.5% salt solution, so that's your initial concentration, 2.5%. Your unknown is V1, because you're being asked how many mil of this stock solution would you need to use to make up a final concentration of 1% in a final volume of 25 ml? So that's your C2 and your V2. So your unknown is over here. You do your rearranging of that equation once again. Yep. So here's your unknown. We want to get rid of this one from that side of the equation. So we can just transfer it so that it's under here. 2.5%. Here's your C1. And get rid of it there. Okay, so now we can solve. We have V1 equals, oh, it's written here actually, V1 equals C2 times V2 divided by C1. In other words, 1% multiplied by 25 mil divided by 2.5%. But of course, before you actually solve for that, you will cancel any like units as such. Check what the remaining unit is. In this case, it's mil. What are you trying to solve for? Volume. Oh, excuse me. So you know you're on the right track. And the answer is 10 mil. So this is quite useful. Those students that are doing wine chemistry one, wine making one this semester, you'll find that Mark Matthews, your lecturer, also likes to use this formula. So it's a good one. Good one to keep in mind. Okay, I'll clear all that. And that is the end of our lecture for tonight. Well done for getting through that. Thank you, everyone. I don't think I've lost anyone. That's terrific. All right, who has questions? Don't go away because I'm going to sign you up for prac class. But before I do that, let me, all right, so I can't move on. That's very interesting. All right, so I'll just stop the recording right there so you can feel free to talk to me. Okay. All right.